some things, but I'll whiz through them because we've already done them, but there are a few little things that I just want to point out in more detail. So let me find my little... Alright, so this PowerPoint I'm going to, so in the past I don't think I've had a PowerPoint, I had bits and pieces. So I've made a PowerPoint about chemical bonding. So are you recording now? Yes. Alright, so why do atoms bond? Classic image. Why do they bond? Because they're trying to achieve a
full outer shell.
Full outer shell. Well done, Maya. A full outer shell. Hence that. Obviously, helium. How many electrons in helium's outer shell? 2. But it's already full. What type of chemical is helium? What group is it in?
Noble gases.
It's a noble gas, so they are already full and very stable. Obviously, hydrogen has 2 as a full outer shell rather than 8, but all the rest of our chemicals that we worry about, it's 8 valence electrons or 8 outer electrons. The types of chemical bonding that we talk about, although we haven't really talked about metallic, we don't really need to worry about that too much, but I'll just mention it briefly, and it is in your notes. So ionic bonding, and I'm going to go into more detail in a moment, is about electron transfer, give and receive electrons. Remember, it's to achieve a full outer shell. Covalent is about electron sharing. You use it, no you use it, no you use it, no you use it. Okay, so they're both nice and close, and they're sharing the electrons, sometimes one, sometimes more, to achieve a full outer shell. And in metallic bonding, it's about free floating electrons resulting in cations or positively charged ions, and then those cations are strongly attracted to the free floating electrons, which are floating around in a bit of a cloud, and that brings those metal atoms together. That's why metals conduct electricity really well, because they have free floating electrons which can move. This little diagram here, you can see here, it's not super clear here, but this atom is giving that electron, so that's ionic. In this one, they're like sharing, they've both got an electron, and they're like, you have it, no, you have it. And in metallic, the idea here is the bat is hitting these electrons out into space, free floating, and they'll both do the same, and then they'll become positively charged and be attracted to all of those electrons floating around in space. So that's the vibe for that little picture. So as I said, you can see here, what's the one on the left got? What's the electron in? A little be mine, like a ring. So here, take this and be mine. Like I said, remember I said memes and cartoon images of chemistry concepts or other concepts beyond science, but in science can actually be really useful in making you understand things. For example, that Homer Simpson, woohoo, 8 valence electrons. Oh, of course, yeah, that's what atoms do or want to do. Oh, oops. So ionic bonding, this is a bit of a recap because we've already done it, but remember it is between metals and non-metals. Metals will readily lose electrons, so they will typically have a small number in their outer shell or small number of valence electrons, like sodium has 1, so they will lose the electrons. Non-metals will gain, so typically they will have a higher number of electrons in their outer shell, and so therefore they're looking to gain some additional ones to fill their outer shell. When we lose and gain electrons, we create new particles called ions, and ions are charged atoms or molecules. Molecules being 2 or more atoms together, can be the same or can be different types of atoms, but the issue is the overall charge being positive or negative. When you lose electrons, you become positively charged because you now have an excess of protons, and you are called a cation. And when you gain electrons, you become negatively charged because you have an excess of electrons, which are negatively charged particles, and you are called an anion. As a result of the donating and receiving, you create these oppositely charged ions, and they are strongly attracted to each other. Positives attracted to negatives, and that's what causes the bonding and the creation of those ionic compounds. I've got 2 images. This one is in the notes. So this is an example of how you would represent the bonding of sodium and chlorine together. We did this the other day when we went through the quiz. In fact, this was the question. So you can see we've got 1 electron in the sodium outer shell, and that's donated to make this outer shell full with 8 electrons. You can see they've done the electronic configuration of the atom in its original format, and then it shows you the electronic configuration after the donation and receiving. And you can see that now, because we've got an extra electron, a missing electron, we are 1 plus charge. We've got an extra electron that we got from sodium, so now we are a negative charge, and those two will be attracted to each other. This image is the same concept, just a different way of presenting it, and it probably shows better the formation of the ionic bond with the attraction between the positive and the negative ions, attraction, etc. I sometimes think it might be useful if you're doing a representation of this is to use different colours or symbols for the electrons of the different atoms. That just means it's easier for you to see which electron came from where. Here is a great cartoon.
So fun.
Sad, sad. How many electrons in this person's outer shell?
7.
7. Here, sir, this is all I have. 1 electron in my outer shell. I don't know why would he be sad still?
Because he's a negative.
Yeah, good. So he's still negative because he's got an excess of negative particles.
So he wasn't negative before, it seems to me.
Yeah, neutral, you're right. The eyebrows. He's positive because he's lost an electron, so he's now got an excess of positive charges. Classic cartoon for learning. Here's another one. Take it in. Got it? So funny. I know. Now, this is another one. So, I just love hanging out with you, chloride. Sodium. Oh no, is that water? What? Where? I'll never forget you. Think about it. Ionic compound. Placed it in water to form a what? What do we call it? No. Aqueous solution. So that's a solution of a solute in water. That's what aqueous means. So when we take a solid ionic compound, like sodium chloride, think about table salt. That's what sodium chloride is. Solid, you can see it. When we put it in water, those ions, the positive and negative components that make up sodium chloride, separate. And we get charged particles in the water, and that allows us to do that dance that we did when we add another chemical into that and create our precipitate reactions. But the essence of this idea is that when you take an ionic compound, even though it's strongly attracted when it's in a solid form, when you put it in water, it will break up into its positive and negative ions. But it might come together when the water's gone. Still might come together as well. Hence the I will never forget you. Nice. Alright. Writing ionic compound formulas. So this is where we use our valency table, remembering that we want to get an equal number of positive charges to negative charges. And the way that we achieve that is we just have multiple atoms. This little puzzle, which is in your notes as well, helps to explain that. So when we're making magnesium fluoride, magnesium is a 2+ ion because it's donated 2 electrons. Fluoride is a 1- ion because it's received 1 extra electron to fill its outer shell. But to make magnesium fluoride, we need just 1 atom of magnesium, but we need 2 atoms of fluorine because they are only 1- charge. So to cancel out the 2 positive prongs, we need 2 of that, and then to write the formula to show what we've got, Mg, 1, but we don't write the 1, fluorine or fluoride, 2 of those fluorine atoms to make MgF2. So I'm not going to go over that anymore because we've done a fair bit on that. Alright, naming ionic compounds, just to clarify, when you're naming ionic compounds, You write the metal first and the non-metal second. The first part of the name is the metal's name. So if it's beryllium, it's beryllium. If it's sodium, it's sodium. The second part of the name is the non-metal or the cation or the anion. And we take the front of it or the stem of it and we add a suffix, which is at the end of the word. We add "ide." So oxygen, if we add oxygen to a ionic compound, we take ox and we put "ide" on the back. Fluorine, we take fluor and we put "ide" on the back. If you didn't remember that, you could just look at your valency table, which has it written there. It's got the names of the various components of chemicals and the symbols. So if you forget that, they're written there anyway for you. So full name of sodium or Na2O is sodium, first name, oxide. Oxygen with the back taken off, replaced with "ide." Again, valency table will help you out. Metallic bonding, I briefly talked about that. So when two metal atoms, or two or more metal atoms, same or different in the form of alloys, combine, we basically form positive ions by these atoms donating electrons. So their valence electrons get released, and instead of being released to somewhere in particular, they just get released into space. So all of those atoms go, valence electrons get off me, and those electrons float around in a bit of a cloud, and all of those positively charged ions that have lost their electrons then get strongly attracted to those free floating electrons, which are spread out all over the place. And that holds the metal atoms in this kind of compact lattice structure, but it is flexible, and it's flexible because those electrons can shift around. So we can make metal into wires, and we can bend those wires. And the reason why we can do that is because of the flexibility of those electrons being like a big cloud that we can just shape into a long blob or a tall blob or a round blob. However we want to structure it, we can, because of the flexibility of that electron cloud. Don't worry too much about this though. They look very happy in their covalent bond. What are they doing with their electrons? They are sharing. And you can see that they've drawn this particular image by putting the electrons not on the shell, but kind of in this shared space, like a Venn diagram sort of. And they're fluorine atoms. They both have 7 in their outer shell. They need an additional 1 to make a full one. So they each share 1 of theirs. So that makes 8 on one side and 8 on the other side at some point in time. So as we said before, covalent bonding is about sharing. Again, our aim is to achieve a full outer shell, and covalent bonding occurs between non-metals and non-metals. We can get covalent bonding between the same type of atom. So here we've got covalent bonding between 2 oxygen atoms, so they're the same type. And we can also get covalent bonding between atoms of different types. So in this one we've got, this is methane, CH4. You can see that we've got carbon and we've got hydrogen atoms. So 2 different types of atoms bonded together covalently. Carbon has 4 in its outer shell. Hydrogen has 1 in its outer shell. Each hydrogen atom is sharing 1 of carbon's valence electrons to give it 2 outer valence electrons, so it's full. And carbon shares 1 from each hydrogen atom to combine with its 4 to create 8, which is full. Now this is the newer stuff. We talked briefly about it, but I've got some notes to give you on this. So Lewis diagrams, sometimes also called electron dot diagrams, so just be familiar with both. We use these diagrams to show how covalent compounds are formed, so to highlight the electron sharing process. We use the symbol for the chemical, so if we were using, say, oxygen, we would put an O, and then we simply represent the electrons in the valence shell. So the valence electrons, the outer ones, we represent them as dots, and we typically will pair them up. Those valence electrons that are shown in the Lewis diagrams or the electron dot diagrams, we call the bonding electrons because they're the ones on the outer shell and they are the most significant. So you can see here, this is how you would do an electron dot diagram or a Lewis diagram for these particular elements. Here is their electron configuration. So you can see that the last number is the outer shell electrons. And you can see that the diagrams do not show the inner shell electrons. They're not relevant because they're not involved in bonding. So for this instance, we only care about the outer ones. We've got one, obviously that's a bit hard to see how you lay it out, but if you go down to chlorine, you can see that we take our 7 electrons, we pair them where we can, we put them in 4 locations, and then if we can't pair them, we just have them as a single dot. And you can see that we generally don't leave a space unattended if we can help it. Obviously this one's different. So even with carbon, we put just 1 in each of the spaces rather than 2 and 2. So when you're representing them on their own, this is generally the fashion. Okay. Here's an example of how you would represent it in the 2 ways that we've been drawing atoms. So when we're doing ionic bonding, we will typically use this format, which is the Bohr-Rutherford diagram. So where we show protons and neutrons, perhaps if asked, then all of the shells containing electrons. You can see that we do a bit of pairing as well. That's just for easy counting and easy drawing. But if you did the same atom in a Lewis diagram, you can see that you just focus on the valence electrons. Same sort of pairing, but you don't include the inners or the protons or the neutrons because they're not involved in the bonding process. Now here is an example of, I'm not going to tell you the name of it because we're going to do that a bit later, but pH3, which is a covalent compound, phosphorus and hydrogen, although hydrogen is a bit of a funny one, non-metals. You can see here we've got the 2 atoms on their own. So phosphorus has 5 valence electrons and hydrogen has 1. We want 8 valence electrons for our phosphorus to be full, and we want 2 for our hydrogen to be full. The way we do that is we get 3 hydrogen atoms. Each of them will share their 1 electron with phosphorus. That will total 8. And each hydrogen atom now has 2 electrons. You can see how we represent that with a Lewis diagram in a bonding format. So we've actually got multiple atoms in there and showing how they bond together. Alright, we mentioned this structural formula, so you can actually use a dash to represent shared electrons. So if we have a single covalent bond, that is 1 electron is shared, 2 electrons is a double, 3 is a triple, and you would represent those with 1, 2 or 3 lines. So in that first one, the one between hydrogen, it's a single electron being shared. In oxygen and oxygen, it's 2 electrons being shared, and in nitrogen and nitrogen bonding together, it is 3 electrons being shared. Here's an example of where we've got hydrogen chloride. This is where 1 electron is being shared, 1 and 1. So hydrogen is sharing 1 with chlorine, and chlorine is sharing 1 with hydrogen. Here is the bonding diagram, and there is the structural formula. So you just use the dash to represent a single electron being shared. In this one, we're sharing 2. So you can see oxygen has 6 electrons in the outer shell, so it needs to share 2 from the other one. And we represent that with a double bond or 2 lines. And nitrogen has 5 electrons in the outer shell, so it needs to share 3. You can see how in the Lewis diagram for the bond, we move around our electrons according to which ones are shared. So we put our shared ones in the middle. So you can see that there are 2 that aren't shared, but then nitrogen will share 3 of its electrons with the other atom. 2 plus 6 equals 8. 2 plus 6 equals 8. We represent those 3 electrons being shared with a triple bond line. Don't stress too much about that. Alright, now this is the bit that's new. We're almost finished. So when we are doing the names and formula of covalent compounds, we use a similar format to our ionic compounds. So we take the name of the first element. So if it was phosphorus, it would be phosphorus. We don't change it. The second element, we use the same format. So we take the name of the element, we take the front half of it, the stem, and we add "ide" to it. So if it was nitrogen, it would be nitride. If it was oxygen, it would be oxide. If it was chlorine, it would be chloride. The only thing that's new with covalent compounds is that we actually use some numerical subscripts to represent how many atoms of each one is present. So in a formula, you would use a little subscript number. Whereas in a covalent compound, when you're naming it, you actually have to show how many atoms are in the name. As opposed to say something like, yes, James, question?
It's all on the dash.
Yes, this will be on the dash, and you're going to get some notes as well. So I've got some type notes to add to the back.
Is it like a practice test with the test from last year that we were on the dash?
I've got some, yeah, I've got one to give you. So last year's test to practice. So for example, if I had magnesium chloride, which is an ionic compound, when I write the name of this, I just write magnesium chloride. Okay? I'm not telling you in the name how many magnesium atoms or how many chlorine atoms. However, in covalent compounds, we actually do. Now, if we were to do this for this particular ionic compound, which we're not going to, but let's pretend that you had to, the way you do it is you use a prefix, a numerical prefix, and you will get these in the test. You don't have to remember them, although some of them are easy. So 1 is mono, 2 is di, 3 is tri. They should be easy. Some of these will be easier because of shapes that you do, like a hexagon. It's got 6 sides. Hexa is 6. Pentagon, 5 sides. Penta. Tetra is 4. That might not be so obvious. Hepta, octa for 8. Probably octagon, probably easy. Nona and deca. Decathlon, 10 events. Might be easy to remember. But you don't need to remember them. They'll be provided. So those are the prefixes. So if, and you don't, but if you did have to show the number of atoms in ionic compounds, what would you call MgCl2? You put it in front. So you might go mono, though generally you leave it off. Monomagnesium. Yeah, good. Okay, but for ionic compounds we don't do that. We do it for covalent compounds. So here is an example. So if we had something with the chemical formula CCl4, what's this compound? C. Carbon and chlorine. Right, there are 2 elements. Sorry, chlorine. So the name of this is going to be the first element name. Now we don't have to write mono. Okay, we just leave it off. Just like we don't write 1 here in our ionic compounds, we just leave it off. We assume that if there's nothing there, it's 1. So it would be carbon. And then because we've got 4 chlorine atoms, we need to put the prefix tetra. And then we need to change slightly the name of that element to chloride. Good. Now the same way that you work out the name of it, you can also work out the formula from the name. Just give me 1 second, James, so I might answer it. I don't know whether I actually did an example. Oh yes, I did. Now, as an example, we might use, oh actually that's not my right one. So I chose this example because I wanted to give you some problems to do, and so I wanted to choose an easy one as my example. So if I gave you the name of a common covalent compound, which was carbon dioxide, now you all know the formula of carbon dioxide because we talk about it a lot. However, if you didn't, if you're an alien coming to the Earth, you would go, right, I can write the chemical formula for carbon dioxide based on the rules of naming covalent compounds. It's going to be, the first element will be carbon. How many do I have of them?
One.
1. Now I could have written monocarbon, but we just don't. That's our rule. And then what element do I have here? Oxygen. And how many do I have? Prefix is 2. Is that right? Yes, it is. James?
How come is there exceptions like with carbon monoxide? Because that's obviously one, so.
Yes, yes. So sometimes we do things just because just the way that we do it. Like we have common names here, for example, water and ammonia. We actually don't name them as per their names. I have a feeling that generally the second part of it, so if the first part is mono, don't put the mono. If the second part is mono, put the mono.
Okay.
Yep. Now, there are some examples of some covalent compounds that we don't actually call by their proper name, but obviously if we did, water would be hydrogen, 2 hydrogens, oxide, 1. That's an example where we don't put a mono. So I'd say it's just, you know how sometimes we do and sometimes we don't? So that one. If you put it, wouldn't be marked wrong, and if you didn't, wouldn't be marked wrong, because it's sort of one of those grey areas. In ammonia, it would be nitrogen trihydride. All right. One little thing to be mindful of is that organic compounds, so those that are made up of carbon and hydrogen, we actually name them differently. So we actually don't call this carbon tetrahydride. We call it methane. So organic compounds have a different naming process, but we're not doing that. So don't worry until you get to probably Year 12 chemistry, where you'll start to do naming of organic compounds. Now, one final thing that I need to talk about, and this is because in the test there's a thing in there and you need to be aware of this. And we've sort of talked about it, but I haven't talked about it explicitly, so I needed to. So remember how when we look at our periodic table, we look at the atomic number and the relative atomic mass, and we use those to work out our protons, neutrons and electrons. The atomic number tells us what? Protons, number of protons, and also electrons. Good. Oxygen has an atomic number of 8, therefore how many protons does it have?
8.
Yes, and only atoms with 8 electrons, so if you found an atom and it had 8 protons, it can only be oxygen. The atomic number is its determining feature. 8 protons is oxygen always. Neutrons are a different matter. So neutrons actually can vary. Yes. And what we do is within any element, there may be different isotopes. An isotope is a variation of that atom that has the same number of protons, because that's its defining feature, the same number of electrons, because we need that for a neutral atom, but it can have varying numbers of neutrons. You know how we've been using relative atomic mass? And so, for example, the relative atomic mass, can somebody read it off for lithium? 5.9, 6.91?
0.941.
Right, so lithium has an atomic number of 3 and a relative atomic mass of 6.91? Is that what it was?
6.4941.
What are you doing? Okay, so the relative atomic mass is actually the average mass of all the isotopes, so all the different variations of lithium that have different numbers of neutrons, averaged out, and it's based on the ratio of those differences. So if you had like a heap of lithium atoms that had 3 protons and 4 neutrons, the atomic mass would be what? 7. Okay? If you had some lithium atoms that had 3 protons and 3 neutrons, the atomic mass would be 6. Now, based on let's assume that these are the only 2 types. Based on the relative atomic mass, given that we use the ratio of these different isotopes to work out this average mass of a collection of lithium, which one do you think we have more of?
The one with 7.
Yeah, the one with 7, because our average is much closer to 7. So the reason why I'm talking about this today is because in the test, instead of you using the relative atomic mass and then rounding it to work out your neutrons, you will be given details on the particular isotope. And the way we represent it is we would write lithium 7, for example. That means that the atomic mass is 7. So you don't need to go and do any rounding and then calculate your neutrons. So if you got lithium 7, that means, using your periodic table, the atomic number is 3. So the protons are 3, the electrons are 3, and the neutrons would be what?
4.
4, good. So this is actually easier. You don't need to do any rounding, you just use the isotope, which is the mass. You subtract the atomic number and that will give you your neutrons. There's a little bit more detail there. So isotopes have varying numbers of neutrons, and those variations and how many of them there are used to calculate the relative atomic mass, which is the average mass of all atoms of that particular element. So we know which isotope we're talking about. We represent it like this, either its name with a dash or the symbol with a dash. That will tell us how many, what the mass is, and then we can calculate the number of neutrons. For example, oxygen 18, how many neutrons? If oxygen has an atomic number of 8, how many neutrons does oxygen 18 have?
10.
10, good. What about oxygen 17?
9.
9, good. Seems straightforward? So it's actually easier than what we've been doing, but I just don't want you to be confused. Question?
Yeah, what's the point of isotopes then?
So the point of isotopes is that they actually exist. So the fact is that even when we talk about atomic number and we talk about number of protons, that is fixed. Oxygen always has 8 protons. However, oxygen atoms that exist in the real world do not always have the same number of neutrons, and that's what an isotope is. And so to kind of make an average, we take all of the possibilities that exist, we work out how many of them there are, use that ratio to calculate the average mass. So if you took a big spoon of oxygen atoms, some of them would have more neutrons than others, but we just average it out. And there are some isotopes that are very stable, and you'll find lots of them, and there are some that are very unstable. Okay, but the main thing that you need to understand is that if you are given the isotope, you have been given the mass already rounded, and you can easily use that to calculate the number of neutrons. Okay.